Is there a laser pointer?
I don't think so.
Okay. Good afternoon. Can everyone hear me okay? Okay, let's zoom out, and we're just going to talk about a very general problem. You have some noisy samples, and you'd like to estimate something. Okay, this is a very ill-posed problem, and so hopefully you'll regularize it in some way. And one approach to regularize it will be to add some constraints. So if you're trying to estimate a high-dimensional vector, you might say, well, I'm only going to believe that k of the coefficients are not 0. Or if you're trying to estimate a decision boundary, you might force the decision boundary to be linear. You don't actually believe that's true, but it's just a nice way to regularize the problem. Another approach is sort of soft constraints. Add some sort of prior. You add a Gaussian prior, you get ridge regression. You add a Laplacian prior, you get lasso. All sorts of examples of approaches you can do there. A third approach to regularize your estimation is to tie a bunch of estimation tasks together. No need for constraints, no necessarily need for prior, just tie a bunch of things together. So this idea dates back at least to the 1950s with Stein estimation, and since then there's been a lot of work in hierarchical Bayesian models that have proven to be very useful. And recently there's been a lot of other multitask learning. And that multitask learning we can sort of think about in the following architecture. So we're going to consider our problem to be estimating t functions. So those are our t tasks. And we're going to assume that we're given some sample input-output pairs for each of those tasks. And so I've got a t domain, input domain spaces, the x's there, t functions mapping those to t output spaces. And what a lot of multitask learning does is it ties together the input spaces. So for example, you might say, let me do some feature selection that is a joint feature selection across all these tasks. So that'd be one way to do multitask learning. A lot of other multitask learning ties together the functions, often by regularizing the function parameters together. What should be obvious from the way I've set this up is that there's a third possibility that we haven't seen people really doing, which is to regularize the outputs together. And in this way, tie the tasks together. And that's what I'm going to focus on in this talk. Okay, so just to give you a little more of a concrete example, let's say we're trying to fit a bunch of linear models. So we're fitting t linear models. Right here is just the empirical error, just the straight least squares fit. And we could add a parametric regularizer. And one possibility would be something like this. So here we've got some side information A that tells us how much task R is similar to task S. And then we're tying together the slope coefficients for R, beta R, to the slope coefficients for the S task, beta S. And we're going to contrast that with this idea of an output regularizer, where instead of tying together beta R and beta S, we're tying together the outputs from the R task and the outputs from the S task. Now, those outputs are still a function of the betas, and that's still what you're solving for. At the end of the day, you want to know what your betas are. But you're sort of just changing what it is that you're trying to regularize. Okay, and here's sort of just the general case. So generally, we'll think of parametric additive regularization. You've got some empirical loss term, and you've got some regularization function J that's regularizing the parameters. Whereas what we'd like to think about is output regularization, where you're regularizing the output values instead. Okay, so we could go a lot of places with this, with all sorts of different regularization functions and all sorts of loss functions. In this talk, we're going to focus on what we think is probably the simplest possible case we could talk about. And one of the reasons for this is that a lot of multitask learning algorithms are being proven to be useful by a lot of experiments. But they can be a little ad hoc, and we wanted to try to start with something very simple where we could actually do some analysis. And this led us to this topic that I'll call multitask averaging. So our function model here is just the constant model. So I've got t random variables, y1 through yt, shown on the bottom there. And you'd like to estimate the means in red. And so there's no inputs here, right, because it's a constant model. And you've been given some data samples in green there. And you'll notice in our model, we don't actually even need to know what we don't need samples from all the tasks. So y3 there, we don't actually have any samples. And just as an example here, we might be trying to estimate, task 1 might be to estimate the average age of first graders, task 2 might be to estimate the average age of second graders, all the way up through averaging, estimating the average age at which people retire. And we'd like to jointly estimate all these tasks. Okay, so if we treated each of these tasks separately, we would just take the sample average, and the sample average minimizes the mean squared error or minimizes the total squared error. So you can write the sample average in this sort of weird way, which is write it as a minimization of the squared error. And the reason we're doing that is because we want to add in this multitask regularizer, where we're going to regularize the outputs or the means, our estimated means, from the different tasks. So again, we'll have some side information, A, which tells us how similar the task R is to task S, and we'll regularize the means to these two tasks. Now, this is a very simple formulation. We haven't been able to find it in the literature, but we don't actually think it's new. But if anyone actually knows a reference of someone doing this, that would be great. We think that what's new here is really sort of our analysis and showing this is going to be really very useful. Okay, so the top line there is just that same objective I just showed you. And the first thing that's nice is in many cases this will be convex and you get a closed form solution. And this closed form solution relies on this A tilde matrix, which is on the right, and this Y tilde vector, which is also on the right. And it relies on this inverse existing. If the inverse doesn't exist, then you might have to actually solve that objective function. If you only have two tasks, then this inverse exists just all the time, so you're good. It doesn't matter how you define A. If you have multiple tasks, then it definitely exists if A has non-negative entries. So if tasks are similar to each other. If you want to say, well, task 2 has similarity -3 to task 4, then this inverse may or may not exist. Okay, the other thing you'll notice about this closed form solution is that Y tilde vector on the right is just a scaled function of the sample averages. And so you've got our estimates, these multitask estimates, Y star, just some matrix inverse times the scale sample averages, so just a linear combination of the sample averages. Well, that's not very satisfying. What you would really like is that they would be a convex combination, right? You would like to know that if I have these sample averages, that I'm basically coming up with a solution that's somewhere in between the sample averages for my task, and not that somewhere way up here. And so we didn't find this trivial to show, and by not trivial, I mean it took us about 3 pages. But you can show that this is, in fact, a convex combination of the sample averages. So you get this sort of warm and fuzzy feeling that if all your samples belong to some convex set, then your estimates are still going to be part of that convex set. Okay, so to give you a little more intuition, we're now going to specialize to just 2 tasks. And we're even going to be even more simple. We're going to look at the symmetric case. Both tasks have the same number of samples, and both tasks have the same variance, as I've sort of tried to depict here on the right. So for that, we can analytically invert that closed form matrix. We get a solution. You can see that's, in fact, a convex average. And the solution will be biased. So your bias has gone up compared to your sample averages, but the variance will be smaller. So, okay, if the bias has gone up and the variance is smaller, what happens to the mean squared error? Well, who knows, right? Luckily, we can give some conditions, and we can show that the mean squared error will be better than what if you just did the sample averages, just each task, if this condition here holds. And that basically means that your means have to be close compared to the variance of your random samples. Right? So every time you draw from this random variable, you're getting stuff all over the place, then regularizing it to another task is useful. But if your variance is very small and your means are far, then this is a really bad idea. So you just have to check that out. And of course, as you have more samples n, then your sort of effective variance goes down, and this is less helpful. And in general, it also shows that if you don't make that task similarity too big, then this is helpful. Which is to say, as usual, you just want to regularize sort of as little as you need to. Okay, so sort of the elephant in the equation here, we just flip back to this equation, is this side information, ARS, or the side information A that tells us how similar 2 tasks are. And this is a big problem in things like this. Now you could say, well, look, that just looks like a regularization parameter. Can't I just cross-validate that? Sure, you can cross-validate it if you have enough data. But often you'd like to believe that there's some side information, or that you could say something about how similar one task is to another. But if you go to an application expert and you're like, can you tell me how similar these 2 tasks are? Say task 1 is estimating average movie prices, and task 2 is estimating the mean age of kids at summer camp. It's like, I don't know, 3? Log 10? I don't know, right? What kind of number are we even looking for here? And you might even notice that there's not even necessarily any sort of semantic similarity between these 2 tasks. And usually when we do multitask learning, we think about semantic similarity. But if you go back to Stein estimation, and I think Efron and Morris do a great job of this in their Scientific American article, they show that with Stein estimation, you can regularize car sales to baseball statistics, and you get better estimates. And similarly here, what's important is not that these are semantically related tasks, but that they're statistically related tasks. And so we can actually analyze in this simple symmetric 2-task case what the optimal side information should look like, or the optimal task similarity. And it should look like the variance over the squared difference of the means. So what that says is that if you have two tasks and their means are close relative to their individual variance, then this is something you should be regularizing hard. Okay, so this gives us a lot of intuition. Now when we go and talk to application experts, we can say, well, what we mean when we ask you how similar these two tasks are is, you know, how far apart do you sort of think they might be compared to the variance of the samples we're going to get. But that's for the symmetric two-task case. If we go to a slightly more complicated case, things get a lot more complicated fast. So here we're going to assume now that we have n1 samples and a variance from our one task and n2 samples and a different variance from our other task. And now that optimal task similarity, instead of just being sigma squared, over the difference of the mean squared, we've got this extra sort of correction factor here. And if you go to more and more tasks, this all gets a little more complicated. But it's still sort of the basic intuition that you can get from the symmetric case, that you want to look at the task variance versus the difference in the means. Also, when we go to symmetric cases, you have to be careful about something, which is that one of these tasks might benefit a lot from the multitask regularization, and the other task might actually lose. Right? So in particular, if you have one task that's really high variance, it has a really crappy estimate. And so when you regularize it to another task that maybe has very little variance, this task wins and this task might actually get corrupted a little. Your total mean squared error will go down, but that also affects how you define the optimal side information. So this is the optimal task similarity if you just care about task 1. If you care about task 2, then you have a optimal task similarity matrix value that's a little different. So let's look at some actual examples. So here's just a simple simulation. So far, we haven't been assuming any distributions. For this simulation, we're going to draw things from Gaussians. So our first task is just a standard normal, and we have 5 samples. And our second task is a normal distribution, and the mean is varying along the x-axis there. That's the mean of the second Gaussian. And we have 10 samples from it and a variance of 0.2. So your total squared error is up around 0.22 there, or 0.23. And what I'm also showing you is this multitask estimate where we've chosen the optimal task similarity either jointly or for the two separately. And you can see that even when your means of these two Gaussians are about 0.4 away, so these are not at all the same tasks, you're still getting about a 50% win. And the other thing I'd like to point out is that this task similarity has nothing to do with covariance, right? These tasks are completely independent, and it happens to be useful to regularize them together. Okay, even when the means are 3 apart, so you know that's like 3 standard deviations away from task 1. So these are really very different tasks, if you will. We're still getting a tiny win over just taking the sample averages. So we're kind of surprised to see that was that useful. Okay, so another way in which this gets complicated is if we look again at those formulas for the optimal task similarity, you might notice in the denominator there's some minus signs there, and it's possible for this optimal task similarity to be negative. And I don't know what that means. I'm not really sure what it means to say that task 1 should be negatively somehow related to task 2. All I can tell you is that sometimes that's the best thing to do. And by sometimes, I mean sometimes in a weird and somewhat random way. So if you look at this task similarity optimal equation and we plot it as n1 changes, then even for this simple example, we can get radically different behavior for different mean differences. Now the actual MSE you get out is very robust. And so you're somewhat robust in general to this setting of the task similarity. But if you really care about the optimal task similarity, it's moving around, maybe negative, can do these kind of funny jumps. So even though we have this very simple formulation, even with 2 tasks, we see this kind of weird behavior. Okay, so that was some simulation. Let's look at an actual problem. So this is sort of broadly useful, right? Because you take sample averages all the time, and sometimes we don't even sort of realize that we're taking sample averages. So in kernel density estimation, it's a smoother. It's basically an average. You've got a bunch of events that have happened. Here I've shown 5 events, and you'd like to estimate the probability at some other event in your domain Z. And you've got some kernel, maybe a Gaussian, for example, and you just smooth the kernel there and regularize it. So it's like you have these events, and you put sort of little kernels down on them, and you sum those up, and you figure out what the probability is at Z. Okay, so this is a smoother. It's basically an average, not of the events xi, but of the function kxi with respect to the parameter z. And so we could equivalently write kernel density estimation as minimizing this squared error, just like we did at the beginning of this talk. And so we can equivalently apply multitask averaging here to form a multitask kernel density estimator. Okay, so this is some work we did in collaboration with the Naval Research Lab. They were interested in estimating the probability of terrorism events. And here we have 7 tasks corresponding to terrorist groups. They have 40,000 locations in Jerusalem. And for each of these locations, they spent a massive effort putting together a data set where they looked at things like, at this location, what's the distance to the nearest McDonald's? What's the distance to the nearest Jewish synagogue? What's the distance to all sorts of things they thought were important? So each location maps to a 74-dimensional feature vector. And in order to get a task similarity matrix, we called up terrorism expert Mohammed Hafez at the Naval Postgraduate School, and he was able to give us some very good numbers here between these terrorist groups. And these are some of the results. So what we do is we leave in all but one event, we form the kernel density estimator, and then we look at the rank of the left out event, and then we switch which event is left out. And what you can see is that, for example, of the 40,000 locations, the left out event was on average the 6,512th event with the kernel density estimation, and now we've moved that up in the rankings to about the 900th event. Okay, so you might say, gee, this is really pessimistic. We're never going to figure out where the terrorists are going to strike. Yeah, we're never going to figure out where the terrorists are going to strike. So these kind of risk maps are more about figuring out, doing things like urban planning and figuring out where you should put the McDonald's, as well as figuring out where to allocate emergency resources and security resources. We're not actually trying to predict where the terrorists are going to strike. So this multitask averaging is really very simple. We've been able to show that under certain circumstances it's going to be good, and you can use this for any smoothing or averaging. We have a number of other applications, but that's kind of boring, so we'll move on, but it does work great in practice. But I started this talk with this bigger story about averaging outputs. And here we're averaging outputs just for this constant model. Can we make this work for anything that's a little more complicated? And the answer is yes, at least a little. What we've done so far is also a multitask local linear regression. So in local linear regression, you've got a bunch of samples as shown on the left in blue. And you're going to go around locally and for each neighborhood fit a line. And this works really well. It's low bias. Accuracy-wise can be really great. But on the right-hand side, as you see, you can end up with these really crunchy functions because there's sort of no way to tie them together at the corners. So here's what that model looks like. You've just got a linear model. And so each of these local neighborhoods that you're going to fit, we consider a task. And then we're going to tie the outputs of these tasks together, which is going to make that function more smooth, is the idea. So this kind of regularization is complementary to other regularizations. So we're using a Tikhonov regularizer here, which is a parametric regularizer, and then we're adding in our output space regularizer. And lots of people here who know how to optimize hard objective functions. In my group, we're not as good at that, so we love closed-form solutions, and we're happy that this one had a closed-form solution again. And so we apply this to color management. In color management, local linear regression with the Tikhonov regularizer is a state-of-the-art way to get good accuracy. And what we see is that adding on this output space regularizer, the mean error is basically the same, but we do in fact decrease the roughness, so that function becomes smoother, which leads you to better color reproduction, which is a really nice thing. Okay, so just to conclude, we're trying to focus on asking, is it helpful and useful and practical to regularize outputs across tasks? So far, we've shown that this can be proved to be good, at least in some cases, and we've seen to show that it's useful in practice. We're excited about this because while the models we've shown are really simple, there's a lot of different things that you could do here. And one of the things that we think is really exciting is that because you're regularizing just the outputs, you don't need the input spaces or the functions to be the same. So in a grand vision of things, you could have one of these tasks could be audio data coming in, and one of these tasks could be video data coming in. And you might have a linear function on your audio data and some sort of latent Dirichlet allocation model, whatever you want, on your video data. It doesn't matter as long as your outputs are somehow comparable, right? Maybe you're trying to figure out estimating prosody or estimating cost or something else that you can compare across the tasks and regularize those outputs together. Okay, and most of what I talked about is available in a paper on arXiv. Thank you.
Any questions? I do have one question. So for example, in the last part when you were regularizing a function, have you thought about perhaps randomly perturbing those neighborhoods in order to obtain a smoothing effect? And would that be useful in that case? And would that be useful also some sort of perturbations of those similarity matrices between tasks in the first part of it?
Yeah, so I think you're asking if we overlap the neighborhoods when we do the local linear regression, if that would help with the smoothness?
Right, or you do it for different neighborhoods which are slightly off from each other and then you average the results or something like that?
Yeah, so in fact we do use overlapping neighborhoods. We use this approach called enclosing neighborhoods, which is a state-of-the-art way to define the local neighborhoods. And so you end up with overlapping neighborhoods already.
Oh,
and we're still able to add some smoothness, yeah. I'm sorry, how does this relate to what regression? To multivariate regression? How does this relate to the local linear part?
Across the groups.
Yeah, so here each of my linear fits is multivariate. I've got here we've got three-dimensional functions that are being fit, many of them being fit independently, and I've got about 800 neighborhoods that we're tying together. Yeah, we're not estimating variance for covariance matrix here. And here, in order to decide how similar our neighborhoods are, we just look at how close those neighborhoods are that we're fitting the planes to. How do we estimate the standard errors of what? Of the beta. We don't estimate the standard errors of our betas. That would be a fine thing to do. Unless I misunderstood your question. Yeah. Yeah, that would be great. Sorry, we've just gotten started.
All right, let's thank the speaker again. And we're